Yeah, it's very hot. Yeah. Yeah. Oh, yeah. You got it. Well, what's that? But listen, I talked to you.
Hey, how's it going? Can you hear me?
Yeah, we can hear you.
Great. Let me see if I can share a screen here and then I can hear you, so that's good as well.
I start legally.
Okay. So can everybody see these slides?
It's on,
Yep.
yeah, so there's one that has the video and one that has the slideshow.
Okay, so I mean on each side, so there's one on each
Yes.
side that can, okay. Okay. I think that should be good. Thanks.
Of course.
Great, thank you.
What's up?
Hey.
I was on.
All right.
Yeah, I'm just gonna stick around for a few minutes to make sure.
Just checking in.
Yep.
I'm almost done with this. Oh, yeah. Yeah, I basically need to take more passes.
Not that question.
And then
Question. How many hours did you spend on it?
Not
you
much,
do
actually.
2 types of
I
wines.
started later than.
No, you didn't.
Yes, I did.
No, you didn't. Started the exact same
I
time.
think you might need to,
Which is my
Really?
business.
Yeah. You started day before yesterday.
because I think you need
Yeah,
a Y to determine
No.
whether
I
or
started on
not
Monday
you're
too.
using the mark at all. And then I think you need a
Yeah.
second Y just
I
to say
didn't even start.
No,
on-
but you worked on it more than I
you're
did yesterday.
fully at X
Last night?
Yes, last night.
No.
No?
No.
Because you can't,
I spent
yeah,
give or take 15
like
hours.
X2 has to be 0 unless
Yeah, 10 to
Definitely.
15.
Definitely
X1 is a certain value.
I, not even.
X2 has to be 0 unless
Five.
Y1, or unless X1 equals.
It's a lie.
15 hours.
At least 10, I'd say.
Yeah.
15 higher upper bound.
Okay, I can see now why you're so.
You can't just, they're not, you can't separately, it's not like this, those two are.
How much?
No, but I mean, I don't know if that's the correct
And he's gonna drop one.
solution, but that
No,
is a
I
legitimate
hope he
problem.
drops
You
the
can't
next
have
one. I
just
don't
an
think
X1
I'm
and an
gonna submit the
X2
next one.
and say X2 can be 5 and X1 can be 0.
What if you in coefficients and trains say it's x1, it's x3?
That won't do it by itself. That won't solve the problem by itself. Yeah, that doesn't solve the problem.
Wait, so you're saying?
Just like, because if you just put it into the machine, like the machine would say, oh, this X2 has a lower, a better parameter, like coefficient associated with it. We're gonna up that and decrease X1.
Oh, interesting. So you're saying like we need somehow to say the machine would make the first.
Yeah.
All that.
Yeah, exactly. There's,
It's very interesting. How the machine knows which are the first ones.
you have to enforce it somehow. I mean, it's weird because if you were just playing the machine, it would make any of this. You would just say like, what is the number? What is the best? Like, what's the number? And do all
I
these
thought that my recollection of the lecture though was like maybe I should just rewatch.
I based on the
He's saying
what you
very-
wrote on the
he said,
board,
yeah,
there were two
like-
Ys.
But there were
No,
two things going on there. There were well actually three, right? It was like fixed cost, a certain level where you couldn't be, and then discount.
It was more difficult problem, smaller. That's why we.
Right. I thought it was actually this, pretty much the same, where it was a fixed cost and then one level of price and then a second level of
That
price.
was 3 levels.
There's a gap though.
Oh, the gap is different.
Right.
We just talked about management science.
Yes.
Yeah.
So you guys are in econometrics, management science, and GMT,
Yeah.
Yeah.
all at the same time.
This is just, you're just
Have
quietly
you've
processing
been through
that.
it, dude, or- yeah.
I
She's
have
like, I've been
I
doing these
have
separately.
machine learning.
Oh,
And it's
interesting,
only
okay.
in
Yes,
the
right.
first ones that have it at both semesters.
Yeah.
Which is so interesting.
I mean-
You guys have it at the same time as management science.
Yes.
Well, I think I think that makes the machine learning easier because they split up.
And you guys have that.
We had it.
Yeah.
Yeah, exactly.
No. We didn't have it.
This looks like kind of interesting, yeah.
Wait, what?
The DAs didn't have the EDA class.
Right.
Yeah.
That was very clearly
It was very new.
It was, no, okay.
Could you check this screen to the?
I don't know. I can try.
We have to go in.
All right, can you guys hear me just to make sure?
Why can we see?
Okay, good.
Yeah, move to this side.
I'll maybe give people a minute or two more to file in and do whichever way they want to, either Zoom or yeah, in the classroom. Hopefully this classroom experiment works. I've the first time I'm teaching remotely while there are people in the classroom. So hopefully this works, but I figured might as well give you guys that, yeah, the opportunity to come into the class. I apologize again for not being there. I'm still testing, faintly, but positive. So I didn't want to give you guys, COVID. So I decided, so I figured I'll teach remotely one more class before yeah, maybe hopefully coming back in person on Monday. Before I get started, I did post on
You need to
Canvas,
still be aware of it.
but I also wanted to kind of let you guys know on Zoom that I'd be really great if you guys could fill out a faculty course evaluation. It's that kind of that the feedback's very important to me, both quantitative, qualitative, just kind of how to better organize the course, how to anything that could help make the course better moving forward. Me not getting COVID the last week would probably be a good one, but that's that's a tough thing. That's a tough thing to be within my control. But that being said, yeah, I'll put the faculty course evaluation link in Zoom. If we have time remaining at the end, I'll give you guys that remaining time perhaps to do the faculty course evaluations here. But anyway, I always give this incentive that if more than 95% of the class fills out the faculty course evaluation, then everybody gets an extra percentage point added to their overall grade. It's kind of just my kind of little, as an economist, that little incentive maybe that would help maybe help get people to fill out these FCEs. It doesn't take long, it shouldn't take long, couple of minutes, and it really does help. Any questions on the previous material before we jump into kind of this last example of kind of pure IV that isn't a randomized control trial?
Professor, can you hear me?
Yep, I can hear you.
For the lecture of last class,
Mhm.
so how do you calculate the reduced form for the domestic violence experiment?
Yeah, absolutely. So let me give you a brief kind of overview of what that was. The domestic violence experiment, people were randomized into 3 assignment into responses. So one was arrest. And then we said coddling was the other kind of assignment where it was either advise or separate. Okay, so the instrument is what you were assigned to do, arrest or coddle, quote unquote. What the treatment was what you actually did, which was arrest or coddle, like what you actually did. And then, yes, you're absolutely right. The outcome variable is reported as an indicator for whether or not we observe a reported repeat offense associated with that case, right? Associated with the case where they either arrested or not, and they were assigned to either arrest or not. So in terms of how we calculate this, in this example, it was just given to us, right? It was just given to us that the sample average of this indicator for the, those who were assigned to coddle was 0.211. So meaning that the proportion of repeat offenses among the assigned to coddle group is 0.211. And the proportion of repeat offenses among those who were assigned to arrest was 0.097. And so that was something that was just given to us. We could have had a table. Let me stop sharing for a brief moment. I could have, in having you guys calculate that, have given you guys a table. Can you guys see the whiteboard?
Yes.
Okay, perfect. So I could have given you guys a table where we had ZI on the x-axis, and I apologize, I know that's not exactly the best Z. So we could have Z on the x-axis, and Y, because Y is a dummy variable and it's the outcome, but it's a dummy variable. I could have given you a table where I gave you this sort of thing and told you, and I'm making up numbers, so this isn't going to correspond to what's in the, what's in the actual slides. I could have said something like, okay, calculate the proportion, right? The proportion for each of these groups of people who reoffended. And how would you do that if I gave you this sort of table? This is just the number of people in each bin who reoffended, who are in this category rather. So how would you calculate those two proportions that were relevant for the reduced form if I gave you this sort of table? I can't see you guys if you raise your hand, so you just have to speak up. So if we wanted to calculate the reduced form effect, what we would do is we would calculate the proportion for z equals to 1. So that would be, if I went here, and again, these aren't going to correspond to what's in the slides. I just made up these numbers. So the proportion that y is equal to 1, given z is equal to 1, well, that's going to be, the denominator is going to be 110 plus 90, and the numerator is going to be 110. Okay. And then, so if I did the same thing for y equals to 0, y equals to 1, but give for those who are in the arrest group, it's going to be 120 divided by 120 plus 100. And so how would I get the reduced form effect from these two, I guess now that I've given you these two numbers? So I guess the question was the reduced form effect, right? The reduced, what is the reduced form effect? What is it's the impact of what on what? Sorry, I don't know if there's an audio problem where if nobody's responding. So the reduced form is the impact of what on what variable on what variable?
The instrument on the outcome.
Perfect. And so if I gave you this four numbers, how would you go about figuring out the reduced form effect?
Take the difference of the two proportions.
Exactly. So that's going to be the reduced form effect, is the difference in these two proportions. Exactly right. So that's basically, how I would have you calculate that on an exam. Either I would give you that table with the numbers and have you calculate the proportions, or I would just give you these two proportions. Does that make sense? Okay. So now let me move on to a new example, an example that isn't based on randomization. So that's that's going to be interesting in the sense that this is the first IB example we've had, which isn't tied to randomization. And this is going to be a paper by Sandra Black and her co-authors in 2015, which is looking to understand the impacts of the Great Migration on the lives of African Americans. Okay. And so the historical context is the authors are going to evaluate cohorts of African Americans born in the South, quote unquote. So South Carolina, Georgia, Alabama, Mississippi, and Louisiana between 1916 and 1932. Sorry, I'm just making sure. Yep, okay, good. It's recording. So note that approximately 40 to 50% of these individuals had migrated out of the South when they were in adulthood. So that's obviously a massive share of African Americans who migrated out of the South. And so kind of no doubt the goal was to improve life prospects by moving to the North, right? And so this was kind of to what extent did it actually improve life's prospects? And the outcome that they're able to get their hands on is, what is the causal impact of migrating from the South to the North on mortality rates after the age of 65? So why do we focus on mortality rates after the age of 65? Well, that's what they can get their hands on in terms of data, because they can get their hands on Social Security records. And obviously that you get Social Security starting when you're 65, so they can see, when did you stop receiving, conditional on having received Social Security, how many years did they receive it? And then therefore, so when did they die post 65? Does that make sense in terms of the data? Okay, so what is the treatment, what is the outcome, and what is the instrument? Just based on this setup slide, can you tell me at least what two out of those three variables are?
outcome is the mortality.
Perfect, perfect. So outcome is the mortality rate. And in fact, they'll have individual level data. So it'll be, did they die or not? So it'll actually even be an indicator of that. And then what about the treatment, or what about the treatment?
Treatment would be if they migrated out of the south.
Perfect, perfect. And this is kind of the classic question. Why can't we just look at the people who migrated out of the south versus those who didn't migrate out of the south, compare their mortality rates, and say, hey, we've got the causal effect of migration on mortality?
Because they were not randomized.
Perfect, right. And so selection, exactly right. So they were not randomized, and therefore selection bias is at play. And that's in the chat as well. So good on everybody. I'm glad, I've hammered that into you guys. So selection bias, right? The people who chose to migrate are different systematically from those who chose not to migrate. Perhaps they were richer, perhaps they were more motivated, perhaps they, perhaps they lived closer to the border between the North and the South. There are countless reasons tied to mortality, but also tied to whether or not somebody chooses to migrate, okay? So we cannot just compare those people who migrated to those who didn't. There's selection bias. So instead, we're going to use an instrumental variables approach. You've answered this question in blue already. Why not just compare those who moved to the north versus those who remain in the south? The instrument is going to be a indicator variable, also called a dummy variable, which is equal to 1. If the individual is born in a town located along a rail line, and is as equal to 0 if the individual is not born in a town located along a rail line, right? And so the decision or the treatment variable is, does the individual live outside of the South as of the age of 65? So did they move from the South to the North by the age of 65? And so now the outcome variable is going to be survival to age 75 among those who are 65. So it's an indicator variable for, did you live to 75? And it's obviously, because you only have Social Security records, conditional on reaching the age of 65. Does that make sense in terms of the instrument, the treatment variable, and the outcome? Okay. So in that case, let's go to what are the kind of 3 assumptions required in order for instrumental variables to be causal?
Independence assumption, exclusion restriction, and
Relevance.
okay, relevance.
Perfect. And so let's go in order. So what is relevance?
Correlation between the instrument Z and the treatment X is
Exactly.
non-zero.
Perfect, perfect. So that the instrument moves the treatment. Exactly right. So that there's some, like you said, correlation between the instrument and the treatment. So in this case, what do you think is kind of the intended? What do you think the instrument is doing? Will those that live along a rail line, do we think they're more, how will that impact migration?
Positively, like if they live closer to the,
Sorry, say
Right.
that again?
just positive correlation, if they live closer to this place, maybe they would more likely to migrate because it's easier for them.
Exactly right. So we think of the instrument as positively correlated, in this case with the treatment. Those who are born in a rail town are probably lower cost and therefore easier to migrate out. Okay. So that's relevance. Now, what about independence? What would that assumption be? I'm going to stop sharing screen for a moment here. So what would independence, what would that assumption require?
That living near a railroad doesn't affect mortality after 65.
Doesn't impact mortality after 65, except
Except the instrument.
Except,
right, except through the treatment, right? So it's that's kind of the independence assumption as well, or sorry, that's the exclusion restriction as well. But basically the point being, the independence assumption is there are no other That's the key point. There are no other factors by which the instrument impacts the outcome. Other kind of omitted factors, I mean, that being not the treatment, right? So the treatment can impact the outcome and the instrument can impact the treatment, but we can't have kind of anything else, right? We cannot have any omitted factors that impact the outcome that are impacted by the instrument. And so let me draw that here. So if we put that there, put that there, put that there. And then obviously, so we have this kind of figure here. I might put yep, okay, good. I might not do this arrow thing, but okay, fine. Now that I've done it, okay. So we see exactly right that the instrument impacts the treatment, impacts the outcome. And so the exclusion restriction, or sorry, yeah, the independence assumption is that there are no other channels, there's no omitted factors that are impacted by the instrument that impact the outcome. Where would I put 1 on this figure, the relevance assumption? Where would that go on this figure?
From Z to D.
Mm-hmm. Perfect. I'm sorry for this childlike drawing here, but that's that's the best I could do on the on this whiteboard that's virtual. And then 3 is 1 plus 2, right? It's saying that the instrument only impacts the outcome through the treatment. So it's this kind of whole thing here. There are right? So it's 1 plus 2. Okay, does that make sense to people? And so exclusion restriction is saying, and what would be in words, what the exclusion restriction is saying for this example here.
There is no other way how living in a railway town will impact the health results unless the person is migrated.
That's right. The only way in which the instrument, the only way in which living in a rail town impacts survival to 75 is through whether or not they migrated. Perfect. Okay. And so this is just showing you a figure of, kind of along a rail line, what the cities are, and then kind of like further away what the cities are. So this is, I think, economic historians like to put these type of figures in just to show, hey, we have to do a lot of work to digitize this. That's kind of the main reason it's in there, I guess, is to kind of say, hey, look, it was a lot of work to digitize these rail maps. But okay, so we talked about this in terms of relevance. That was the first assumption, independence assumption, and exclusion restriction. What are potential violations of the assumptions 2 or 3? So come up with some examples. What could be potential violations in this context of, say, the second assumption or the third assumption?
Like a railway town might have more just general kind of traffic through it, meaning more economic growth, and if that's correlated with health outcomes and how long you live, that could be a potential effect.
Perfect. I like that. So if you being born along a rail town, if rail towns are just richer systematically than non-rail towns, then in childhood you might have had better access to better nutrition, be higher income, have more money, and all of that is another channel by which in later life you might be less likely to die. It could improve your health relative to those who don't live in rail towns, and that might have nothing to do with migration or not, right? It's just a factor by which rail town impacts health, but that has nothing to do with kind of the treatment, which is whether or not you migrated. Okay. I see one in chat, which is air pollution, which is near and dear to my heart. Not air pollution itself, but studying. I'm not like a fan of air pollution, but I basically there, the point being that if you live in a rail town, you're more exposed to air pollution. Air pollution has been shown to decrease respiratory and cardiovascular health. So you might be less likely to live to 75, conditional on 65, not because of migrating, but because of the pollution associated with living in a rail town relative to not. So does that make sense? I mean, I'll ask for other factors, other examples, if people can come up with them. Economic prosperity was one, air pollution was another, but basically coming up with factors by which rail town affects health that has nothing to do with migration. Does anybody want to come up with another example? No worries if not. Okay, so much of the paper is devoted to a discussion of kind of like these assumptions, and economic prosperity does come up. So they do things like, oh, well, I mean, and we'll talk about this a little later, we'll control for income, we'll control for, we'll try to pick cities that are also not, are similarly wealthy, that type of thing. But they'll have some discussion, but you're right to the point being we haven't randomized the instrument, so there are other things that could impact the outcome that are not. I mean even that like it's much more tenuous, these assumptions 2 or 3, than in the case where we randomized the instrument, right? It's harder to come up with examples when the instrument is randomized as to how the instrument might impact the outcome that has nothing to do with it. Here it's a little bit easier, right? Because we think of migration as being, we think about living along a rail town as being correlated with stuff. Okay. I'll ask you guys, who are the never takers, who are the always takers, who are the compliers in this example? So what are never takers, what are always takers, and what are compliers?
Always takers are ones that would always die in old age, regardless of being born in a railway town.
The old age is the outcome. So it's not tied to the outcome, it's tied to the.
So they would find a way to move even if they weren't in a rail town.
Perfect.
Never takers, even if they were in a rail town, would not move, and then compliers would not move if not near railroad, but would if so.
There we go. Perfect. Okay. Yeah, so that's exactly right. So never takers are people who would not migrate, regardless of whether they lived in a rail town or not. Always takers would be people who would migrate, regardless of whether they lived along a rail line or not. And compliers would move if they lived along a rail line, and they would choose not to move if they didn't live along a rail line. Okay, so they are moved by the instrument, right? That's the key point. So good there. So this is just saying that what I just said, right? The never takers, which we'll call Ni equal to 1, always takers Ai equal to 1, and compliers. Right. This is all this is exactly what we just said. So authors calculate the sample average, or at least an estimate of the population expectation of Y0i and Y1i where possible. What would Y0i be and what will Y1i be in this example? If we're going back to our potential outcomes framework, forget about the instrument for a second, what would be kind of the potential outcome we're interested in?
The average age.
Yeah, sorry, close. Yeah, so the average age of death, or in this case, whether or not they died by age 75. And what would Y1i be then? Whether or not they died if they migrated. And this would be whether or not they died if they didn't migrate. Does that make sense? So we would love to have the causal effect Y1i minus Y0i. Unfortunately, we don't observe both of those outcomes, right? We only observe if they did migrate, which one of these two would we observe?
Y1i.
y1i, and if they didn't migrate, we would observe y0i. Exactly. So here, this is just another way to kind of show the IV results. This is kind of the probability of survival. You can think about it as the proportion who survived to 75 conditional on 65 among the never takers, among the always takers, and then among the compliers. Okay. And so let me ask first, for the never takers, why can't we estimate the population expectation of the case where they did migrate, what their probability of survival would be?
Usually don't migrate.
They didn't. Exactly right. They don't migrate. So in the sample, you would never observe a never taker who did migrate, because that's by definition not going to happen. Always takers, same thing. We would never observe a scenario where they wouldn't migrate. And because we don't observe that scenario, we can't estimate the proportion of the people who died by age 75 among, the non-migrators, because there aren't for the always takers. So what is the IV estimate? What would be the, just intuitively, what might be the IV estimate for this example? First of all, the IV estimate is the impact of what on what. And then second of all, who is it? Yeah, I guess I'll ask that first. Who is the, what is, so if I say, what is the local average treatment effect, or what is the IV estimate? What is it's the effect of what on what in this example? Anybody want to take a crack at that?
Being close to a rail line on mortality, it's 75.
So that would be the reduced form effect, right? So that would be the reduced form effect. What is the impact of living along a rail town on mortality, right? Did they live to 75 or not? What would be, so then that's the reduced form. What would be the first stage? I can ask that. What would be the first stage effect?
Migration on rail line or the opposite? I'm not.
Yeah. No, yeah, that's right. So it's the impact. So it'd be rail town on migration on rail town is how I would say it. But basically the point being that it's the impact of living near a rail town on migration. Okay. And then, so what does that mean the IV estimate is? What is or the treatment effect or the local average treatment effect? What would that's the impact of what on what? What, which variable? Sorry, go for it. Anybody? So it's going to be the impact of the treatment on the outcome. So in this case, it's the impact of migration on whether or not you live to 75. And who does that estimate apply to? Out of the never takers, always takers, and compliers, who does the local average treatment effect apply to? Who does it not apply to?
Compliers only.
Right. So the IV estimate only applies to compliers. It does not apply to never takers or always takers. So based on that intuition, how might you think to estimate the local average treatment effect given this kind of these estimates here? And again, these are the sample proportions in each of these bins of the case where the sample average, in this case, of those who died beyond at age 75 in the never takers group.
Should we just subtract the compliers? Like,
exactly. So you'd want to subtract this from this, right? So in let's see if sorry, okay, I don't know how to write on my slides, so I will just do it here. So in math terms, it's going to be the expectation of y 1i minus the expectation of y 0i, given that you're a complier. that's the local average treatment effect. That's, the reduced, so, right, which we know from before is reduced form over first stage. Okay. So that's, so I kind of cut out of this version of the class a proof of this, but you can prove that the local average treatment effect, so conditioning on being a complier, what is the average difference in potential outcomes, is just the reduced form over the first stage, right? Is the IV estimate we've been talking about. Does that make sense?
We use like IV estimate and this local average treatment effect as synonyms, right?
That's right. That's right. Yeah, that's a good point. Yeah, so exactly right. Yeah. So yeah, so this is an interpretation of the IV estimate or the local average treatment effect, which is equal to reduced form of the first stage, is that it's an estimate of the causal effect, the treatment effect for the complier. Does that make sense to people? Okay. So let me now go back to sharing slides here. Okay. So if we subtracted these two numbers, well, I guess what would we get? We would get a 7 here and a 2, so it's 0.027. Okay. And so, but it's negative 0.027. So what would that indicate? It indicates that migrating leads to a reduction in survival. So it's actually the opposite from what we'd expect, right? So, because the outcome variable is 1 if they survive to age 75 among those who are 65. So so do you see the point here that it's a negative effect, right? So those who migrate among the compliers are less likely to survive. Does that make sense? At least kind of what's going on there. And so why might we think that, so that at least intuitively, that's the opposite of what people expected, right? People expected migrating to be positively associated with old age mortality. Or sorry, migrating to be negatively associated with positive. Oh my God. Okay, let me take a step back. So we expect that if you migrate, you're more like it's going to improve health and you're less likely to die by 75. Right? But we're seeing the opposite here. And so does anybody have an intuition perhaps for why that might be?
Stating cells died prior to 65.
That's one potential thing, right? They were it could be that so I'll go idea by idea. One is that yes, this is compliers, and so the never takers and the always takers, the estimate does not apply to them, and so the people who didn't migrate might have died before 65, right? So the fact that living to 65 is already a pretty big, I mean, certainly over in the sample period they're considering, is already a pretty substantial event, right? Especially for, African Americans and during the sample period. So it might be that, yes, conditional on living to 65, you're less likely to survive to 75. But that doesn't necessarily mean that you're less likely to live to 65. That's one. Another explanation that's in the chat is that maybe, our prior is that there's more discrimination in the South than the North. Could be that it's the opposite, right? It could actually be that there was more discrimination and de facto segregation in the North, or, at least in terms of how it affected my mortality, that it affected mortality more in the North. Are there any other explanations that people can come up with as to why that's a negative effect? Why we're seeing that migration corresponds to a lower survival probability?
people migrating could have a lesser standard of living upon migration because, like, just finding housing or like jobs could be difficult, and therefore with like a lower economic situation, like, the health could have been impacted.
Yeah, that could be that. So we think of migration as probably, in terms of what we think it is we think that African Americans were hoping to improve their life prospects by moving north. So we think they have better job opportunities, better economic prospects, that type of thing. That might not be true. It might also be true in terms of social networks, or, like, I'm living in the South, my family's lived in the South, my friends live in the South. If you move to the North, maybe those social networks aren't as prevalent, and it's kind of harder to make your way in the North than it was in the South. Yeah, so there are a lot of different explanations, but it was kind of a very puzzling finding when it came out. Why are we seeing lower survival rates among the compliers who migrated relative to those who didn't migrate? Okay. Does that make sense in terms of this setup, how to kind of interpret it within the instrumental variables that we learned, and then also, kind of what the results are there? Any
Can I
questions?
ask, so the use of the instrument here would rule out an explanation such as like a family that moves must have been in a more desperate situation back in the South, and so
Oh, well, sorry, go ahead.
like, does that rule out that that would be a kind of selection bias? But I think that is taken care of by the instrument. Is that right?
So yeah, so if you believe the assumptions that the only way in which living in a rail town impacts the outcome, which is old age mortality, is through whether or not they choose to migrate, then yes, I think you would be ruling out that those who live in a rail town are systematically more, I guess, you would be ruling out that those who move are more desperate in more desperate circumstances than those who don't move. Because you're kind of saying we're using the variation and whether or not they move based on whether they live in a rail town. So what would be an issue for the assumptions would be if there were differentially more people who are desperate to move in a rail town than not. That might be kind of a different factor that impacts whether they, impacts health, but doesn't necessarily have, isn't tied just to migration, but is also tied to health directly. Does that make sense?
Yep, thanks.
Yeah. So the key point is So the key point is these three assumptions, right? These have to hold, but if they do hold, then we can rule out kind of other selection bias factors, right? That there are differences across those who migrate and those who choose not to migrate that would drive the effect. Okay. Okay, so it's, just kind of this very controversial finding that people who migrate seem to be positively selected in terms of old age mortality. And again, this is an estimate that only applies to the compliers, and it's an estimate that you have to believe these three assumptions in order to believe it's causal. Okay, so we can poke a lot of holes into these three assumptions, and we can, I think, poke a lot of holes perhaps into the into saying, well, the external validity isn't going to be there, right? The people who choose to move, in either case, there could be a very different outcome. People who choose not to move in either case could be very different outcome. And the outcome variable, did you survive to 75 conditional on living to 65, isn't exactly the best one, right? Because people might not have lived to 65 to begin with if they didn't move. Okay. So that is the last IV example. I'll close by talking about two-stage least squares. And then after that, I'm hoping on Monday to do kind of a review, and then on Wednesday to do, maybe a more informal kind of, practice questions, put up exams and kind of see if you guys have any questions type thing, because you won't have recitation. Friday will be the last recitation before the exam. Okay. So that's kind of the plan for the remainder of the course. The exam will be on not this coming Friday, but the next Friday. Sorry, let me see if I can open up this. There we go. Okay. So we learned how IV estimation can give us the causal effect of treatment on outcome. In particular, it gives a local average treatment effect. What does it mean to be a local average treatment effect? Well, it's the effect of treatment on outcome only for the compliers. Okay. So this lecture is going to focus on how to incorporate IV into a regression context. So not just, before we've been talking about 0-1 instrument, 0-1 treatment, and kind of how that works. Now we're going to kind of expand it to, well, what about if the instrument is not a 0-1? What about if we have multiple instruments? What about if we want to control for factors and then, and then still do instrumental variables? Okay. So this is still, we're talking about before the IV regression. It's the reduced form over the first stage, which gives you the local average treatment effect. This is kind of in Greek letters, and this is in words. And we can easily form such estimates by using something called two-stage least squares. Two-stage least squares regression. And the advantage of 2SLS over IV that we've talked about thus far is that it allows you to estimate more general models as well. Cases where we have more than one instrument, cases when we want to include covariates in the analysis. So we don't necessarily think the three assumptions hold just unconditionally, but once you control on some relevant omitted factors, then we think the instrumental variables assumptions do hold. Does that make sense? So let's go into what two-stage least squares is. Two-stage least squares, and this is just going back to our example where we had a binary instrument, so meaning 0-1 variable for the instrument. In that case, we can estimate a reduced form equation, right? And this is the old way of doing it. This is the way we talked about before. So the old way of doing it is to estimate the reduced form. The reduced form will give you this rho, right, which is the difference in population averages of the outcome among those, well, in the example, KIP who won the lottery minus the population average of the outcome in the case where they lost the lottery. In general, it's when the instrument's equal to 1 and the instrument's equal to 0. So what would be an example of the reduced form regression in the KIP example that we talked about first? What would be the regression you would run if you're trying to do the reduced form regression in a case where, in that case where the KIP was kind of that case, that KIP setting? So maybe I'll take, yep, in the chat, let's see here. Yeah, so exactly right. So it would be, the outcome variable would be test scores, and the instrument would be what's the independent variable, which is whether or not you won the lottery. Okay. Now we can estimate the first stage as well. And what would be the first stage in the example, the KIP example? So in this first stage, what would be the first stage regression in the case where, we have that KIP setting?
Of winning the lottery, attending
On what?
the effect of winning the lottery, going to KIP.
Exactly right. Exactly right. So it's the dependent variable is did you go to KIP or not, and then the independent variable is did you win the lottery or not. And so you estimate that regression, and you're going to get this psi. Okay, and so that's what we learned so far, right? We learned, you can estimate the reduced form regression, you can estimate the first stage regression, divide rho by psi, and that's what you get. You get the local average treatment effect. Okay. we can do it a different way, which is actually estimate the first stage regression. So again, it's going to, in the example, the KIP example, it would be, did you go to KIP on whether or not you won the lottery? And then now you're going to construct the fitted values or the predicted values of that regression. Next, you're going to estimate the regression, what's going to be called the second stage regression. The second stage regression is going to be the outcome. Now it's going to be not on the actual treatment variable, but on the predicted treatment variable, the fitted values from the first stage. And it turns out you're going to get exactly the same coefficient estimate as the first kind of way we did it here. Okay. And so what is the intuition behind two-stage least squares? Well, does anybody want to take a stab at what they think the intuition is? Okay. So basically what we're trying to do is we're saying, well, take this regression. How does the instrument impact the treatment? And then this fitted value is saying, keep only that variation in the treatment. So the treatment, this DI could move for a lot of different reasons. People could go to KIP for a lot of different reasons. That's an E1I. But one of the reasons is the instrument, right? They could choose, if they won the lottery, they might go to KIP more likely than if they lost the lottery. So this DI hat is capturing only the variation in KIP attendance generated by did they win the lottery or not. It's throwing out all of those other sources of variation that lead to whether somebody went to KIP or not. And then we're saying, okay, using that variation in the treatment generated by did they win the lottery or not, what is the impact of treatment on outcome? In this case, what would be the outcome impact of predicted KIP attendance on test scores? Does that make sense? Okay. So we didn't talk about standard errors here for this example. We won't really talk about standard errors too much for this way of doing things either. The one thing I want you to note is that if you actually did this in Stata and you ran the first stage, you got the fitted values, you ran the regression, you would get the right coefficient estimate, but you would get the wrong standard errors. And the reason you would get the wrong standard errors is because this is a predicted regressor. So that means that this also has sampling variability associated with it. That's kind of the broad point. It doesn't, I'm not going to test how to actually calculate the right standard errors using two-stage least squares. It's in the book in page 144. The one thing I will test on is if you were to run this first stage and then second stage, will you get the right coefficient? And will you get the right standard error? And so you will get the right coefficient estimate, but the standard errors will not be standard errors that you can use if you ran this first stage regression and then ran this second stage regression. Does that make sense to people as to why that is? Okay. So unfortunately, unlike ordinary least squares, two-stage least squares is subject to finite sample bias. That's basically saying that in small samples, this lambda hat, the thing you estimate, isn't going to be, the expectation isn't going to be equal to the true lambda. It's not an unbiased estimator. That's not important. The real thing that's important is that this problem is especially acute if there's a weak first stage. And a weak first stage means a first stage that is not statistically significant. Okay, So, you know, you can think about in the KIP example, if it turned out that winning the lottery didn't really affect KIP attendance, you're gonna have big problems with two-stage least squares. And so it's common to check whether or not in the one-dimensional case, the t statistic is sufficiently high, but in the multiple coefficients version, where you have more instruments than one, it's common to check whether the F statistic is at least 10. Okay. And again, the F statistic is just an extension of the T statistic. It's used to test whether multiple coefficients are equal to 0. We would use the T statistic in this example where there was only one coefficient in the first stage. Right, so we would just test whether this was statistically significant or not. Does that make sense? I know I'm going quickly over things. I just want to, please do slow me down if there are any questions on this. Anybody? Okay. So that's it. I mean, what I guess I'll say is I'll repeat again what we're doing is we're estimating a first stage with this regression, form the fitted values, and then estimating what is the impact of the fitted values for the treatment on the outcome. And in statistical packages like Stata, this process is automated. You're not going to actually have to do the first stage or the second stage. You can just actually estimate two-stage least squares. But you know, so you don't really have to estimate it this way, where you actually estimate the first stage and then you estimate the second stage. Stata will give you kind of the automated IV regret or two-stage least squares regression, and will give you the right standard errors. And so a nice thing to add about two-stage least squares is that it's easy to add additional control variables and to consider multiple instruments. So this is the case where we just have one instrument and we have no control variables. You can see that it would be easy here to add instrumental instrumental variables and to add control variables. Okay. Yeah, go for it.
What when you say form fitted values di hat, what is the process of, because I mean, I guess DI is a series of numbers based on the regression, right? So what are the fitted values are just like the results of doing this regression with your ZI data set?
Yeah, so let me do that there. So if I go to the whiteboard, I'm going to go ahead and clear. So yeah, so we're going to have data. Let me go here. So we're going to have data on D, or on, well, I mean, for what's important, we're going to have data on D and Z, right? We'll also have data on Y, but that's not relevant for the first stage. And so what we're going to do is, so D is going to be in this example. Oh my God, this is going to be it's going to be more annoying than I thought. Okay. So it's going to be 1, right? It's going to be 0. It could, there could be another 0. There could be another 1. So
You can copy the text box with option grab.
Or maybe you could do just hit enter.
oh yeah, that's better. That is better. Okay. So from now on, I'll do that. So, and then we might have also for the instrument, the same thing. Maybe I'll just make the space better. Okay. Right. And so the point being, so that's data. And so if we ran a regression where this was the dependent variable and this was the outcome, or this was the independent variable.
Pretty strong inverse relationship right there.
Yeah, no, I think exactly right. I think I screwed that. Well, I mean, it's not associated with the KIP example, but it. So let's say we have alpha plus, what did I call it? Rho times Z plus, yeah, this is a inverse relationship, exactly right. So what we would do is we would say, give us the predicted value d hat, which is going to be alpha hat plus rho hat times z. Right, so you're going to estimate this regression. You're going to get a constant term and you're going to get a rho term. Those are going to be your coefficient estimates. And then you're just going to predict based on that one regressor z, what would be d hat. And it doesn't, yeah. Does that make sense?
Right, so that gets you to one number d hat.
No, depending on, so it's going to be depending on the z, right?
Oh, right. Sorry.
So yeah, so let's see if I can do this. So let's say our alpha hat was, let's say alpha, let me go here. Let's say alpha hat was equal to 0.02 and then rho hat, oh my goodness, there we go. And rho hat was equal to negative 0.4, right? So then d hat would be equal to, in the case where it was 0.02, in the case where it was equal to 1, well, it would be negative 0.38. Does that make sense?
Yep.
Okay, so that would be, so yeah, so it's going to be d hat is going to be if there's n observations in your data set, there's going to be n of these d hats, depending on which observation. And obviously in this simple example, there's only 2 possible values that d hat can take.
Yeah.
But I mean, if z is continuous, then obviously it'll be different for each observation. Does that make sense?
Yeah.
Good. Sorry for that agonizing creating of a table there. It's been a while since I taught in Zoom, but let me jump back in. Okay. So yeah, so that's another key thing in this kind of two-stage least squares example is we don't necessarily have to think of z as being 0 or 1. We don't have to think of d as being 0 or 1. We could think about z and d as being continuous variables. We would have a similar kind of instrumental variable assumptions in order for the resulting lambda hat to be causal, but it would not be restricted to the kind of that setup we've been talking about so far. Does that make sense? Okay. So now in the remaining time I have, I'll just go over 2 examples of two-stage least squares. One is just going to be really quick, and then one I'll kind of go into a little more detail. This first one's going to be really quick. So large literature investigates the extent to which education improves health outcomes. So, those with more education, are they more likely to, live longer? Do they have lower cholesterol? Blah, blah, blah. A lot of different health outcomes. The focus of this one was BMI. So why can't we just, I want to hear it loud and proud. Why can't we hear it? Why can't we just look at people who have more education versus those who have less education and compare their health?
Because it's not randomized.
Selection
There
bias.
we go. Exactly right. It's not randomized, and therefore there will be selection bias into who chooses to get more education or less. And those selection bias terms could also be correlated with health, right? People who are have higher income, may be more likely to be educated, maybe more likely to have better health for reasons tied to their income rather than the education. So perfect. Okay. So that's good. So we've now kind of at least realized why we can't just run a regression. We at least have to do something else. This is going to be, we're going to use an instrumental variables, obviously. And the instrument they're going to choose is the compulsory schooling laws. So what they're going to look at is people, for example, who before had to only go to 10th grade. They were forced to go up through 10th grade, and then afterwards you can drop out if you want or not. Okay. And then they're going to compare to people who, after a compulsory schooling law change, now you have to go to 11th grade. That's the law. So now the people are going to drop out 11th grade, not at 10th grade. So look at how that one additional year of education that's driven by the law change, how does that impact body mass index, BMI? Does that make sense in terms of what the instrument is, what the treatment is, and what the outcome is? Maybe if we look at this table, it'll be a little clearer. Well, here, the treatment variable is going to be years of schooling. The outcome variable is going to be BMI. And, and it's going to be, you could see that they've got country level data here. Well, not country level data, but they've got data from a lot of different countries. So they've got, survey here. They've got, different surveys. They've got the year of the birth, country specific second order polynomial and age they've controlled for. But the point being that what they're using as the instrument is, was there, was it before or was it after a compulsory schooling law change? How does that impact years of schooling? And then how does that years of schooling impact your body mass index? Okay. What might be a violation of the instrumental variables assumption required to think of this as causal? So the instrument being, were you born before or after a change in the compulsory schooling law change? Years of schooling is the treatment variable, and obviously the outcome is your body mass index. What might be a violation of one of the IV assumptions in that example? I guess what are the IV assumptions in this example? What would be the first one? Like just in terms of, what do we term that first one? The first IV assumption?
Whether your relevance.
Relevance, exactly right. Perfect. And in this case, what would that assumption be?
Whether you are born before or after the schooling laws is going to impact years of schooling.
Perfect. So whether you were born before or after that compulsory schooling law change impacts your years of schooling. So that's going to be a very selected set of compliers, right? It's going to be the people who would have dropped out of 10th grade before and now they drop out at 11th, right? So those are going to be the compliers in this kind of example. What would be the exclusion restriction? So let's forget about the independence assumption for now. Let's just go straight to the exclusion restriction. What would be
The year you're born won't really affect your BMI
except through
this cutoff of schooling.
Except through your years of schooling, exactly right. So whether you're born before or after the compulsory schooling law change doesn't impact your health, other than through your changes in number of years of schooling. Okay. And so what might be an example of a violation of that assumption?
Just over time, their BMI changes generation to generation, maybe.
Could be, because people are getting healthier over time. So people who are born earlier have worse health for just other reasons. And then the people who were born later have better health, just systematically health improves over time. It could be that the compulsory schooling law change might have come with other kind of changes in policy that were tied to health or tied to other things that would impact health. So they're kind of, think of these kind of omitted factors by which the instrument impacts the outcome that has nothing to do with the treatment. A violation could be that there are differences in BMI based on what age cohort you're in. Exactly right. So that was going back to people who were born earlier, perhaps just are systematically in worse health, just, for reasons that are not related to their years of schooling. Okay. So that's kind of one very simple example, not simple, but one kind of example of a two-stage least squares analysis. I'm going to close by talking about this kind of example here, where it's the effect of family CEO on firm performance. And so here, they're going to look at successions. So the treatment variable is the CEO dies. Do I choose to appoint somebody from the family, or do I choose to appoint an external CEO? So these are family-run businesses. The the family owner dies, and so they decide, am I going to give it to one of my kids essentially, or am I going to give it to an external CEO? So the instrument for this thing is going to be the gender of the departing CEO's firstborn child. We think of that as being somewhat random, right? Was the firstborn child a male, female, somewhat random? And the thought, so that's good news in terms of the instrument. And then families where the first child is a boy are more likely to have a family CEO succession. So that's what stage is that evidence of?
First stage.
First stage. Exactly right. So that's evidence. And what assumption, IB assumption, does that kind of give us evidence in favor of?
Relevance.
Relevance, exactly right. So the instrument in this case is, was the firstborn child a boy or a girl? The treatment is, did they appoint a family CEO or an external CEO? And then they're going to look at a bunch of kind of firm level outcomes in terms of performance. And the main finding is that family successions in this IB framework have a large negative causal impact on firm performance. Causal if you believe the IB assumption. So operating profitability on assets falls by at least 4 percentage points after the CEO transition. Family CEO underperformance is particularly large. So this effect is particularly large in fast-growing industries, right? Where maybe experience matters a lot, like adapting matters a lot. So like industries with highly skilled labor force and relatively large firms, okay, which might be tougher to run. Okay. So the first stage is going to be, again, as I mentioned, an indicator variable for, is the incoming CEO related by blood or marriage to the departing CEO? 0 otherwise. And then we're going to have the gender of the firstborn child as the relevant independent variable. So this is the impact of the instrument on the treatment. So we're going to estimate this first stage regression and then say, plug in the predicted treatment into this regression and say the second stage regression is, what is the impact of on firm performance of whether or not it was a incoming CEOs related by blood or marriage predicted by the gender of the firstborn child. Does that make sense? The setup here. And so what would be the reduced form regression associated with this setup? Does anybody remember what the reduced form regression would be?
The effect of gender first on YI.
Mm-hmm. Exactly right. So what is the effect of having a boy first on firm performance? Now, in terms of compliers, never takers, always takers, who would be the compliers and who would be the never takers and who would be the always takers? Who would be the never takers?
The first kid is a boy and he didn't got the CEO position in the company.
That's right. So it's going to be the first stage. So sorry, the never takers are going to be regardless of if the firstborn child is a boy or a girl, they're not going to appoint a family CEO. What would be the always takers?
First child is not male and they do appoint a family CEO.
I mean, so you want to think about it as never takers being regardless of whether it's a boy or a girl. Yeah, sorry, go for it.
Oh, fair. Yep.
Yeah, so regardless of whether it's a boy or a girl, they're not going to appoint. Always takers would appoint a family CEO. Doesn't matter if it's a boy or a girl. And again, I mean, it's by blood or marriage. So some of these people will appoint their wife, or they'll appoint, their cousin or something like that. That would still count as a family CEO. Wouldn't be tied to whether it was a firstborn, it was a male or female, but yeah, would be a family CEO. What would be the compliers?
Appoint a family CEO if it's a boy.
Yeah. And don't appoint a family CEO if it's the firstborn is a girl. Exactly. And so this IV estimate is going to apply to who? Which of those three categories? Perfect. If I had to ask you, so Tim Cook is the CEO of Apple. Which of these categories would Tim Cook be in? Very likely, at least. Of those three that I mentioned. Never takers, always takers, compliers.
Never takers, I guess.
Never takers, right? Apple, I mean, it's probably not even, it's not his decision even, but certainly whether or not Tim Cook's firstborn is a boy or a girl, he's not going to get to appoint the CEO of Apple to be his son or daughter. So yeah, so they're in the never taker category. So you could start to think about what type of firms would be compliers in this framework, right? And which type of firms would not be compliers, would be never takers or always takers. Okay. So this is a table of results. I was going to ask you what it was, but it says first stage there, so it would be more of a test of reading comprehension than the econometrics. But so the dependent variable is whether or not it was a family CEO, right? So 1 if they're a family CEO, 0 otherwise. And then this is the key instrumental variable, right? Gender of the firstborn child is male. And you can see that there's a systematically positive relationship between gender of the firstborn child is male and family CEO. And that's true regardless of, they added kind of other control variables, the male child being do they have a male child, number of male children? These are other kind of instruments they considered. Ratio of male to total children. They added in kind of log asset values, firm age. The point being that there's a systematic and persistent, no matter what control variables you put in, relationship between gender of the firstborn being a male and the proportion and whether or not they appoint a family CEO or not. Okay. Does that make sense? So that's the first stage. This is OLS. OLS means just run the impact of the treatment on the outcome. So in this case, it would be family CEO. Did they appoint a family CEO on differences in operating profitability around the CEO succession? Okay. And so are these OLS estimates, the impact of appointing a family CEO on differences in operating profitability, are these causal effects 1 through 4? So this is just the OLS regression, normal regression of family CEO on profitability. No, right? And why not? Exactly. Omitted variable. Yeah, family CEO is not randomized. And so it's not, there's omitted variable bias, right? There are other factors that could explain both the appointing of a family CEO and profitability. Okay. That being said, you can see here that just if you look at that correlation between family CEO and profitability, you're seeing that there is a negative relationship between appointing a family CEO and operating profitability. Okay. Whereas we're seeing, if you do the IV estimates, right now we're instrumenting for family CEO with gender of the firstborn. You continue to see, you see a smaller, perhaps, well, about the same size, depending on which specification you look at, you do see that there's a relationship between family CEO and profitability. So appointing a family CEO corresponds to, I believe this is in dollars. Does it say where? Sorry, I'm just trying to see. Oh no, it's okay. No, you can interpret it as percentages. It's OROA, which is, I mean, we don't need to get into the finance of that, but you could interpret it as basically a 6% decrease in profitability. Okay. So family CEO, if you believe the assumptions, causes a 6% decline in profitability. It would be an odd example, but can somebody come up with an example of why one of the three instrumental variables assumptions might not hold? Does anybody have any kind of examples of why, yeah, one of the three instrumental variables assumptions might not hold? Anybody want to take a shot at it? So what is the instrument? What is the treatment? What is the outcome? Well, the instrument is gender of the departing CEO's firstborn child. Treatment is, did they appoint a family CEO? And outcome is operating performance. Just think profitability of the firm.
There might be a pre-existing connection between the instrumental variable and the outcome.
Could be like what might be an example of the pre-existing connection?
Well, if you're the type of firm to make decisions based on nepotism, then you might be running your firm not as well in general.
So that's potentially an external validity concern, meaning that, in this example, the instrumental variables only applies to the compliers, and the compliers are the ones that exactly right. Are going to, if the firstborn is a male, have a family CEO. If the firstborn is not a male, not do a family CEO. So what you're saying is kind of an external validity concern, that the type of firms where they're compliers, the type of firms that are compliers are kind of a very selected set of firms. It's not necessarily going to be the, most well-run firms. You'd have to think through an example where how well they run the firm is tied to whether or not the firstborn is a male or not. That would be an example of a kind of violation of the instrumental variable.
Okay.
Assumption. Does that make sense?
Yeah, I think I was just mixing up which was the instrument and which was the treatment.
Yeah. So it would be something like the firstborn is a male, and so they decide, the existing owner decides to run the company better, like invest more assets in the company than if the firstborn was a woman, was a girl. Okay. Like that would be kind of a violation of the assumption. Why? Because the instrument impacts the outcome, firm profitability, through another channel, just how many resources are invested in the company, even before kind of the family CEO decision is made. Right. That would be a violation of that assumption. Does that make sense?
Yes, but that's probably not happening.
Yes. I mean, that's exactly that. I mean, so that it's kind of more of an art than a science in terms of, do we think these three assumptions hold or not? So if you kind of believe that that's not happening, or you believe that there are other, like those assumptions are unlikely to be violated, we're in good shape in terms of causality. Okay, and so that's the last point I did want to bring up in terms of IV, and it's kind of right on time here, is that internal validity is when an estimation strategy successfully uncovers the causal effect we're interested in. So in terms of the assumption, if the assumptions don't hold, that'd be a violation of internal validity. Whereas external validity is, can we use this IV estimate in other settings? Well, we can't use it for never takers, we can't use it for compliers, and we might not be able to use it in other countries, right? That are not part of this sample here. Okay, so that's kind of the external validity versus internal validity, right? In terms of external validity in IV world, you can't apply it to never takers, you can't apply it to always takers, and you can't apply it to other settings, which is always the case. And then internal validity is, does the IV estimate, is it even causal, right? Can we believe these three assumptions? Does that make sense? I think I'm on time here at 3:20. So I'll stop here. All right, so I'll see you guys. I'm really hoping in person on Monday. I think it'll be in person on Monday. All right, so I'll see you guys then.
Thank you.
Thanks.
Feel better.
Oh, I forgot to mention, please do fill out the faculty course evaluations if you get the chance. I really do. I really would appreciate it.
The middle topic of that.
Sorry, go for it.
Yes.
Do you want me to log out of this Zoom and into the next one for the next class?
Sure. Yeah.
Cool.
Can I ask a question about the homework assignment before you go?
Oh yeah, go for it.
I just hold on, let me pull up my assignment. When we're interpreting the like treatment effect coefficients, are we supposed to be also in like giving the value of the constant too, or do you want us just to give whether like, for example, like the incentive like with commitment is statistically significant, or should we say the constant is also statistically significant?
No, so we care about just the beta 1 hat and or the beta 2 hat, depending on
Okay,
the question.
so like when you ask for the treatment effects, I don't need to give the constant or the treatment effects. I don't need to give the constant value. I only just give the two beta 1 and beta 0, and then say whether or not either of those are statistically significant.
Perfect.
And then I had one other question. When you ask us to I don't know if you know the questions in C part 2, in 1C part 2, it asks like, did you expect this result? And I explained it like, we expect the result because we would expect like over time people would become less motivated or committed to go to the gym. That's why the coefficients decrease. Is that like an okay interpretation of why I would expect this result, or am I supposed to be explaining it in a different way?
No, I think that's a reasonable explanation for why you might expect, the treatment effect of, incentivizing people or even having commitment contract to go down over time.
Okay, and then just one more too. For the when we're looking at one of the questions is we're changing from the constant to the control in terms of the intercept. How come like we see that there's like an increase in the other coefficients, so like incentive, like in beta 1 and beta 0, but we see that the constant and the control intercept still stays the same?
Sorry,
If that makes sense.
Yeah,
So like one of the questions is we're like replacing, we eliminate the constant term in the regression model and replace it with an indicator variable for the control group. So we see that the intercept for the constant in the control group still stay the same, but then we see that the incentive and like the incentive with commitment, they increase. So is there a way that we have to explain like why we see an increase in their coefficients for beta 1 and beta 0?
Yeah, exactly. So you want to think about what each of those coefficients are capturing in terms of differences in means versus the mean itself, and think about like, okay, are we estimating the sample mean? What group are we estimating the difference in sample means across? What groups are we, and you'll see kind of algebraically why kind of some of the coefficients change, some of them don't, and what they change to.
Yes, I guess I don't know what you mean when we're moving from a constant term and then replacing it with an indicator variable for the control group. Like, what does it mean? Like from the constant term to the indicator in the control group?
So so instead of having a constant term, which is just a column of ones, what we're going to do is replace that column of ones, get rid of that column of ones, and add a column which is, are you in the control group or not?
Okay.
And so now you want to think about, when each of these variables is 1 or 0, what does that mean in terms of the what the coefficient is capturing?
Okay, so now that we're, instead of having constants like 1, we're changing it to 1 or 0, and then that, based on why it's 1 or 0, like then we explain how that affects the coefficients of beta 1 and beta 0.
That's right. And what, like, and I would kind of, the hint of it is, think about the sample averages of the control group, think about the sample average of the treatment group, and think about like what, you know, what is being captured in the coefficient in each case.
Okay. I guess I kind of get it. I'm so a little confused. I just like, I don't, because you asked us to compare them. So like all I just said was that they increase when you eliminate the constant variable, but I don't understand like why it increased.
Yeah, so I think you'll need to dig. I don't want to give you too much more.
Yeah,
If you want to
yeah.
come to the office hours tomorrow, maybe I'll give you another hint. But like think
Okay.
about just in a basic model with alpha plus like just with one dummy variable in there. What is the beta capturing? What is the alpha capturing? Maybe look back in the notes, the slide, the lecture notes. And
Okay.
what is the alpha? What is the beta capturing in a case where it's just yi equals alpha plus beta di plus the error term.
Okay. Okay. And then, sorry, one more question. I think I got it right, but I just wanted to make sure, like based on today. So when we determine whether or not like an instrument is a good fit for like whatever we're like in our experiment, we base it whether or not the instrument meets the 3 assumptions that we're talking about, right? So like
Yeah,
it,
in terms of whether the IV estimate is causal.
yeah,
that'll come
yeah.
down to,
So like,
those
because
three
I think the second question is like, should we use like the CEO letter as an instrument for the training program? Would it be useful to use this? So I explained it using like, and I explained it using like the relevance assumption, the exclusion restriction, and then also the independence assumption. Is that like a correct way to explain?
Yeah, I think so. You want to,
Okay.
exactly right. You want to think about, is B versus C more likely to, you know, yeah, for those assumptions to hold or not.
Okay.
Exactly. I think
Thank you. Sorry, I had a lot of questions.
No, absolutely not.
Okay, thank you.
Yep, see you. Bye.
Bye.
All right, see you guys.